Okay. Hi everyone, my name is James, and today I'll be talking about the impact of cache architecture and interface on performance area of FPGA-based processor parallel-accelerator systems. So this work is part of a larger project called LegUp, as Stefan was previously talking about. It's an open source high-level synthesis tool which compiles C to Verilog. We target a hybrid processor accelerator system where it comprises of a soft mixed processor with hardware accelerators that are generated from LegUp. And there's option to also compile the entire program to hardware, which was the method that Stefan was stating. And it's freely downloadable at www.legup.org. So this is the default system target architecture by LegUp. You can see the MIPS processor connect to the other components over the Avalon interconnect, which is Altera's bus interface. The interconnection network here is generated by the SOPC builder. So if you see the colors, but so the MIPS processor communicates with the hardware accelerators to start the accelerators, to send over the arguments, to see if they're done and retrieve any return values if necessary. And there are two modes of execution in LegUp. First is the sequential case, where either the processor or a single accelerator can run at a time, or we can also run them all in parallel, as in this case. And whenever the processor or the accelerator accesses memory, it first goes to the on-chip cache. Now, if it's a cache hit, the data is returned to the requester in a single cycle. And if it's not, then the on-chip cache accesses the off-chip DDR2 memory to burst to fetch a cache line. Now, inside the on-chip cache, there's a dual port memory. Now, one port is reserved for the processor as it has different control signals from all of the accelerators. So all of the hardware accelerators end up sharing the second port here. And the arbitration at this point is created by the SOPC builder, which works in a round-robin manner. Also note that each accelerator can have its own local accelerator memories for any data that is not shared between accelerators or the processor. So this work will be largely talking about that portion of the figure, the on-chip data cache. We look at how to architect the cache to improve the performance of the application. So the underlying motivation for this work is that we all know off-chip memory access is very slow, and even though that FPGA is just maybe the greatest thing in the world, we cannot avoid this fact. So we can implement caches on FPGAs to reduce memory access times, but different cache architectures can bring different results, and application performance can largely depend on the cache architecture and its interface. So with this study, we would like to answer the following question, which is, given multiple accelerators, how should the cache and its interface be architected to maximize application performance? To do this, we use a shared memory model, as shown in the first figure, where there's an on-chip data cache backed by off-chip DDR2 memory. The advantage of this method is its simplicity, as coherency schemes are not needed, which cause latency and area. But the disadvantage is that contention can exist when multiple accelerators want to access the memory at the same time. But we also look at how to mitigate this fact in the study. In implementing caches, there are properties which are unique to FPGAs. Muxes take up a lot of area, which can impact Fmax significantly. And in caches, muxes are used to select a word from a cache line. So with bigger cache lines, muxes sizes will also increase as well. They're also used in set-associated caches to select between the different sets. Now, FPGAs have these on-chip block RAMs, which have up to 2 ports, which means that there can be up to 2 reads or 2 writes at any given point in time. But what's more interesting is that these on-chip block RAMs can run very fast, and oftentimes much faster than the speed of the overall system. So we take this to our advantage in the system. So in this work, we introduced 2 multi-ported cache designs, first of which is based on the live out cable proposed by Eric Forrest, and second, where we use a multi-pumping memory, where the memory is clocked at twice the system clock of the system. And using these multi-ported caches, we investigate 3 traditional cache parameters, which is a cache size, line size, associativity, and to see how they affect performance. Now, there has been quite some work on memory architecture for FPGA-based computing. To list a couple, there's recent work by Jason Kong from UCLA, which partitions the global memory address space into different memory banks. And each partition is implemented as its own memory bank. So so that to allow multiple access to separate memory banks. There's another work by Ang from Imperial College, which implements a multi-ported cache, also with memory partitioning, and each partition is implemented into a subcache. So this allows multiple concurrent accesses to different subbanks or subcaches, but if they access the same subcache, the accesses have to be serialized. Now we take a different approach from these works in that we don't have to partition the memory space at all. So let's look at how the first multi-ported cache works. So this was based on the live value table approach, but we actually modified it according to our needs. And in implementing this as a cache, we were able to reduce the memory consumption to less than half of the original work, which I can talk about more later if anyone has more questions on that. So each one of these memory blocks is a true dual-ported memory, so that each port can do either a read or a write. And the idea is that each port has to connect to each other port through one block of memory. So you see here that port 1 connects to port 2 through M1. Port 1 connects to port 3 through M3. And port 1 connects to port 4 through M4. This enables any data that is written by port 1 to be readable by all other ports, and vice versa. So the operation itself is very similar to the original work. Whenever you do a write, let's say port 1 wants to do a write, it will write to all the memory blocks that it's connected to. And it will write to the live value table that for that given address, port 1 is the most recent writer. Now let's say port 2 later wants to read from the same memory address. It will read from all the memories that it's connected to. And it will look up that address in the live value table, which will tell that port 1 is the most recent writer. So it will take the data that is from the memory that is shared with port 1, which is M1 in this case. So we make this into a cache by attaching a memory controller at each one of the ports, which subsequently connects to either a processor or accelerator. So due to replication, this cache scales with the following equation. And you can see that a 4-ported cache can be created by 6x amount of memories. And we call this the LVT cache. Now the second approach is based on multi-pumping, where the memory is pumped at twice the clock speed of the system, as you can see in the figure. This also shows a 4-ported cache, where the 4 accesses are divided into 2 sets. So the first set accesses the memory directly in the first clock cycle of the faster clock, whereas the second set is registered. Now in the second clock cycle of the faster clock, the data will be returned, which is saved into a different set of registers. And now the second set accesses the memory. So at the end of the second clock cycle of the faster clock, all 4 accesses are done. So from the system's perspective, you can see that 4 accesses are done in one clock cycle of the slower clock cycle. And the advantage of this method is that it does not replicate memory size at all, because it is one piece of memory. But it has a caveat that the system has to be slow enough so that the memory can be pumped at twice the clock speed of the system. And we call this the MP cache. So both the LVT and the MP caches allow concurrent access from all of its ports to all regions of memory, or all regions of the cache, sorry, every cycle, which is what differentiates our work from any of the prior works. So using these multi-ported caches, we created 5 different architectures to be evaluated. The first one is a sequential dual port. This was the default architecture, where a single accelerator is running that performs all the work in the program. Now the second one is the parallel dual port, where there's 6 parallel accelerators running, but they share one port into the cache. And the third one and the fourth one is a parallel 4-port, either using one of the LVT or the MP caches. In this case, 2 accelerators share one port into the cache. And the 7-ported cache using the LVT. This one, each accelerator owns its own port into the cache. And only the LVT cache can be used for this method, because in our system, the MP cache cannot be clocked more than twice the system clock. So we used 6 accelerators for this study because we wanted to vary the amount of contention to the cache from very high to medium to none. So you can see also that when the ports are shared, the arbitration is created by the SOPC builders, so it works in a round-robin manner when they access at the same time. For each one of these architectures, we evaluated 16 different cache configurations, 4 different cache sizes, and for each cache size, 4 different line sizes. And as the line size increases, the number of lines in the cache also decreases accordingly. Sorry. And we also evaluated the direct map cache versus two-way set associated cache. We used 9 memory-intensive data parallel benchmarks. And by data parallel, I mean that no two accelerators ever write to the same piece of same memory location, but they can read from the same memory location. And each of these benchmarks come from a variety of categories with different input data sizes. We use models and functional simulation to extract the total execution cycles and quarters for area and timing results. This was synthesized for the Stratix 4 on the D4. And with all of the architectures and cache configurations, it took a total of 1,440 model simulations plus quarter synthesis, which probably would have taken until at the end of my PhD if I had run it on my computer. But we have access to an amazing piece of machine called Skynet. For those of you who don't know, it's a supercomputer that is maintained by U of T. I believe it's the top 61 in the world right now. And all the results that I'll be showing in the next pages are normalized against the baseline system, which is a sequential system running a single accelerator with a 2 kilobyte cache, 32 byte line size, and uses a direct map cache. And the results for the baseline system are shown in the table. So let's first look at the geomean execution time. So at the horizontal axis, we see the 4 different cache sizes. Each cache size shows 4 different line sizes. And the vertical shows the speed up ratio versus the baseline. You can see that there are 10 different graphs on this page. The top 2 show the sequential case where a single accelerator is running. This is also connected to a dual port memory. And the parallel dual port case where the 6 accelerators are connected to 1 port of memory. This is a 4-ported cache using the MP method, 4-ported cache using the LVT method, and 7-ported cache using the LVT method. And the one-way and the two-way indicate the direct map versus set associated cache. So you can see that the best result is exhibited by the 7-ported cache with the 6.14x speed up versus the baseline. And the second best result is using the 4-port MP cache with the 6.0x speed up, so it comes very closely to the best result. And in the graph, you can clearly see 2 clusters of data here, with the top cluster showing the data for the multi-ported caches, and the bottom cluster showing the dual-ported caches. And you can see that the performance varies a lot with different cache architectures. What's more interesting to note here is that the performance decreases for smaller cache sizes after 64 byte line size, and for bigger cache sizes after 128 byte size. So we can see this effect in both in terms of execution cycles and Fmax. So let's first look at the execution cycles. Similar effect is exhibited here, 64 byte line size for smaller cache sizes. This occurs because there's a lot of conflict misses which occur because too many blocks map onto the same cache line. So for example, for the 2 kilobyte cache with the 256 byte line size, there's actually only 8 cache lines in the entire cache. So this makes the probability of the cache line being evicted much higher. So when multiple accelerator access the cache at the same time, this can cause cache thrashing to occur, where the same set of cache lines are continuously evicted and fetched. So this effect is mitigated as you go to bigger cache sizes. You can see for the 16 kilobyte cache, the performance increases for the bigger line sizes. Now let's look at the Fmax. You can see that there's a general trend where as we go from bigger cache line sizes, the Fmax drops. This is because as you increase the line size, the multiplexes which is required to select the word from the cache line increases as well. And the most notable drop is for the two-way set associated caches because they require the most amount of multiplexing. It muxes on the inputs and outputs of the sets, and within each set, there's a multi-ported caches which require multiplexing as well. Let's look at the area results. Shows a similar trend to the Fmax. The area increases with bigger line sizes because due to more multiplexers needed. And the biggest areas are shown for the 7-ported LVT caches because they have the most amount of replication, and with each replication, there's another set of muxes introduced. Interesting to note here is that point there shows the architecture which showed the best result in geomean, and that shows the second best result. So you can see that the error is almost half for the second best result compared to the best result. In terms of memory consumption, as expected, the LVT methods increase memory consumption. And for the 7-port LVT, the memory blows up the most. This memory consumption shows the total memory of the entire system, which includes the data cache, instruction cache, any local accelerator memories. That's why the ratios are not constant with increasing cache sizes. But note that for all of the MP caches, the memory stays constant. So I'd like to highlight a couple of per benchmark results. You can see for the dot product and the histogram benchmarks, the top one shows the worst result for that benchmark. Second one shows the best result. This one shows the best architecture in geomean and second best architecture in geomean. And only the parallel architectures were considered for this table to isolate any gain from parallelization of the benchmark. So you can see that even between just parallel benchmarks, the speed up can vary very widely. This is because this architecture has a very big cache thrashing effect as described earlier. And for the histogram benchmark, it doesn't show as much sensitivity to memory, but note that the MP cache actually shows higher speed up than the LVT cache in this method. So in conclusion, you can see that performance varied widely with different cache architectures, and there is no single cache architecture that exhibits the best result in all the cases. And in terms of FPGAs, excessive muxing impact the Fmax significantly, which causes most of the two-way systems to lose in a lot of cases. But multi-pumping does show very promising results, and even though the 7-port LVT showed the best result, the 4-port MP comes very close with approximately half of the area and cache size which is 21x smaller. Future work will be to combine this method with the memory partitioning approach to allow a larger number of accelerators and processors. So that's it for this talk. Questions?
He smells pizza. Is there any question?
Yeah.
So if I saw correctly, you got the best speed up from generally the best speed ups from a cache architecture that did not get you the highest Fmax, right? I didn't quite see where the Fmax of the 7 LVT and the 4 MP were,
Right.
but I presume that they were not at the top or at the bottom, right?
Yes.
And yet you got the greatest speed up.
Yeah.
So this is purely from reduction in contention.
Yes.
Okay.
And all of the benchmarks were designed to be very memory intensive. So for the other architectures, that would show a lot of contention to access the data.
Okay, any others? Okay. Oh,
Do you know what the miss penalty is for missing the crash?
So in our system, it's approximately, I believe it's 24 cycles to fetch the first 256 bits. And then it works on bursts, so every additional cycle after that fetches another 256 bits.
And it caches it as a single cycle?
Yeah, yes.
okay, great.